Okay, here we go. Forward elimination. So our strategy is we want to with a forward elimination, we want to eliminate all the zeros below the main diagonal, right? So eliminate, not eliminate the zeros, eliminate coefficients, i.e. set to 0, below main diagonal of the matrix. So how does this work? So let's start with writing out our matrix. I'm just going to rewrite the linear system here. So we have 1, 1, 1 in the first row, 2, 1, 3, 3, 1, 6 times x1, x2, x3 equals to 4, 7, 2. All right, so my first step in forward elimination. So I want to, like I said, I want to eliminate these coefficients, right? I want these 3 here to be 0. These are the 3 that are below the main diagonal. How do I make them 0? So let's figure out the first one here. So let's zero out element A 2, 1, right? That's the element of A in the second row, first column. Let's zero out A2, 1. How would I do that? I'm going to find some coefficient, some multiplier, to multiply that first row by. So I'm going to call this multiplier lambda 2, 1. And lambda 2, 1 is defined as the thing I want to zero out, A2, 1, divided by the main diagonal element A1, 1. So what is this? What's the value of this lambda here? It's 2 over 1, or 2. I guess I should say 2 over 1, right? Just to illustrate where this is all coming from. 2 over 1, right? So my lambda is 2, right? Let me go ahead and write out in words what I just said about what lambda is. This lambda is the element, ELT element, I want to zero out divided by the diagonal entry. So that's my lambda. So I'm going to take that lambda and I'm going to multiply that onto the second row, onto the first row, and then subtract the first row from the second row, and then replace the second row. Okay, so basically, replace the second row by times plus a negative lambda. In other words, new 2 equals to old 2 minus lambda 2, 1 times 1. Which will give me, now the first row doesn't change, right? Furthermore, the third row didn't change either. The only thing that got replaced was the second row. I'm tired of writing the column vector x, so I'm just going to write it like this. And the first and third elements of B didn't change. But the middle row changed, right? Because I did the operation on it. So the new 2 equals to the old 2 minus lambda times the first equation, and that gives me a 0, just like I had planned, a minus 1, a 1, and a minus 1. Okay, so now I've zeroed out that element. That's great. That's bringing me one step closer to this forward elimination process being done. Okay, but I need to do the same thing again now for this final element in the first column. Again. Right, so now I have another lambda. So lambda 3, 1 equals to A31 over A11. Right? So that's now 3 over 1, or 3. And so now I have another row operation to do, while my new 3 is equal to the old 3 minus lambda 31 times 1. Let me write that out. That was fast. So new 3 equals to old 3 minus lambda 31 times 1. Okay, so now I have my first equation didn't change. That's still 1, 1, 1. My second one didn't change from what I wrote last time. Anyway. By the way, I'm tired of writing this x equals thing. I'm going to do this thing called an augmented matrix. Okay, so instead of writing the 3 by 3 matrix that times x equals to some other column vector, I'm just going to smush the column vector onto the matrix. And the way that works typically is people will just put a dotted vertical line here, and then write your b vector here. Okay, this is what's known as an augmented matrix. Let me write that out. And the thing about the augmented matrix, the reason why it works, is because through all these row operations, we do nothing to x. X just stays the same. So why write it over and over and over again? But the dashed vertical line shows me that this to the right of the vertical line is not actually part of my matrix. It's part of my knowns. Okay, but that's okay. All right. So so my new 3. My new 3 is my old 3 minus lambda 31 times my first equation. So 3, 1, 6 turns into 0, negative 2, 3, and my last element of b becomes 10. All right. So now I'm almost done. I have one element left, and that's now in the second column. Right. So I'm done with the first column. All of my elements below the main diagonal in the first column are now 0, and I want to eliminate this guy right here. So this one here, to eliminate that. Is it what? Negative 10? The question is it negative 10? It might be negative 10. I might have accidentally scratched out the negative sign in my notes. So, thanks. Is it actually negative 10? Can we confirm? Negative 10, everybody? Negative 10? All right, negative 10. Sorry about that. Thank you for pointing that out. Negative 10. Right here. Okay, what was I saying? All right, so let's knock out this last one right here. Let's knock out this last one. And to do that, I'm going to define my lambda 32 equals to element A32 divided by the element of the main diagonal. It's not A11 anymore, because now I'm in the second column. So the main diagonal element in the second column is A22. So it's negative 2 over negative 1, or 2. Okay, so finally, to end my final step in this Gaussian elimination here, my new 3 equals old 3 minus lambda 32 times 2. Giving me, finally, well, my first row didn't change, right? My second row didn't change. My third row now becomes 0, 0, 1, negative 8. Now what's nice about this, I've done forward elimination, and now I can basically read directly off of here what is my final the answer, the value of my final variable. By the way, this didn't have to be a 1. That last element there in the third row didn't have to be a 1. It could have been something else. like let's say it was a 2, then the answer for x3 would be -4. Instead, it is a 1, and so the answer is -8, but it didn't have to be. It just sort of ended up that way, right, in this example. Okay, so that's my forward elimination. It was complicated. I had to figure out these lambdas. I had to do a division. I had to do a multiplication. I had to do a row operation where I added everything together. And there's some computational cost associated with it. But it's an algorithm that's very straightforward. You can kind of march through it, unless your numbers are really wacky. Like if you have 10 to the 6, let's scroll back up here. Like these numbers are nice, right? These nice small integers. But if in my example, if this is like 10 to the 6, and this is like 10 to the minus 13, like weird stuff is going to happen, right? When I divide them, or the other way around. Like if this is 10 to the minus 6, and this is 10 to the plus 13, then this lambda is going to be 10 to the 19, right? So weird stuff's going to happen, right? And you might start to get weird rounding errors. Okay, so that's forward elimination.